I'm going to assume that I have a current carries, that's what we talked about now, so I'm going to skip that as well. Okay, here. Assume that I have a magnet, a strong magnet, Hussein. I have a strong magnet. And I'm going to put in here a wire that carries a current. And I would like to know what happens when I put a wire carries a current inside that magnet. So that's the experiment that we do. So we say that a wire carries a current is nothing but a flow of charges. So if you have a wire, magnet, the two walls are magnet, and you have, so the magnetic field is in that direction, and you have a current, a wire carries a current, and the current is flowing in that direction. So the wire or the current inside the wire is nothing but charges. Positive charge will move in that direction. What happens then? So what happens is each charge of those will feel a force in the upward direction. And the whole wire will move up in the upward direction. So if we have a wire carries a current inside the magnetic field, there will be a force, magnetic force on that wire. And we really need to know how much is that force, the magnitude of that force. So what we do is, what I did is, I'm going to assume that a small part of the wire will have a force F. That small part has an amount of a charge equal to, can anyone guess how much charges are equal in that part of the wire? How many charges? Because we know that the force acting on one charge, equal to Q V times B, assuming that the motion and the magnetic field are perpendicular to each other. So this is the force acting on one charge. That piece of wire, if I'm able to find out how many charges are there, then I will be able to find how much is the force acting on that piece of wire, right? So simply, how many charges? It's the number of charges per unit volume times the volume. Times the volume. This is the number of charges inside that piece of wire.
And GQ.
The N number of charges per unit volume, this is the property of any material. It's tabulated, we will know it. It's well known. Now, what is the volume of that piece of wire? Rami. So what is the volume of that piece of wire? Area, which is whatever the cross section is, times the length. No, this is the number of charges inside that wire. Each one carries a charge of Q. So this is the total charge in here. So it's going to be N times A times L times QV cross P. I will keep the cross for now. Keep the cross. Tariq said that. Tariq is saying actually we studied something like this before. Let's see it. Oh. Tariq is going to give us from his background. He said that J equal to NQ times
We just lost في الA تقريبا.
in the QV, drift velocity, V. Is that right?
It had something to do
I over A.
had something to do with cover.
Yeah, and equal actually J. That's the current density. That's I over A. So actually, this is that can give us information about I, which is equal to N number of charges per unit volume times the area times Q times V. NAQ times V. So that's the current. That's the current. This is the definition of the current. Look at that equation. The force in that piece of wire equal to NA times the length, this is the volume, times Q times V cross P. N, A, V and Q, I can replace those four terms and put instead of them current. Then the force on that piece of wire equal to the current times the length cross P. Times the length of that wire cross P. It's I, L cross P. Someone will ask, well, is the length a vector? Actually, no. The length has also information about the direction of the motion of the current inside that wire. That's very important. That's why we assume that it's a vector. And the direction here is the direction of the current. So it's I times L cross P, where L is a vector that carries information about the direction of the current. So, and this is the law. If you now have a force, if you have a current in a wire, and that wire has a length L, and if you put it inside a magnetic field, then the force on that wire will equal to ILP. IL cross P. Good. Now I have a wire, piece of wire, and I'm gonna form it as a rectangular. I'm gonna form from that wire a rectangular, and that's the rectangle that you see. And I will put inside that, that rectangle in a magnetic field. I'll assume that that rectangle has a current that flows clockwise. So the current in that rectangle is actually flowing clockwise. What is the net force acting on that wire? How do you know that it's zero? Remember, force. No. Force on a wire carries current equal to I times L cross V. Keep that in mind. Which means that equation tells us that the force has to be perpendicular to both of the direction of the current and the magnetic field. So let's now take a segment. I will take the upper segment. The upper segment. What is the direction of the force on that upper segment? Up. What is the magnitude of the force on that upper segment? ILP. I times L times B. I will take the lower one, the bottom one. What is the direction of the force? It's down. What is the magnitude of that force? ILP. Two equal forces and opposite direction. They cancel out. So the top and the bottom one, the forces on them, they cancel out. How about the two side ones? Same thing. Same magnitude, opposite direction, you get zero force. So the net force in here is going to be zero. Now let's assume that we have the same loop, that loop, the same thing, but now I put it that way inside the magnetic field. So the magnetic field is going in that direction, and I put the loop in that way, that direction, that case. So what happens? Guys, you have to imagine this. This is a three-dimensional problem. So we have to imagine it together. So that's the loop. And let's assume that this is the loop. I put it that way, and this is the magnetic field. Wire. I bend it as a rectangular. So I call that a loop. So there is nothing in between. This is just the border of this. A wire around this. So now this is the loop, hey guys, and the direction of the magnetic field is from the right, that wall to that wall. This is the direction of the magnetic field. Now let's calculate the forces on this. That side. What is the direction of the magnetic force on that side? Up. How about this? Down. This. This is the direction of motion. Oh, okay, again. This is the current is flowing in that direction. So the force is up. The force in here is going to be, the current is flowing down. And this is the direction of the magnetic field from that wall to that wall. So the force is along that direction. So if you put if you put this in that case, like this, the net force on it is equal to 0. Now I'm going to do this. This is the direction of the current, of the magnetic field. That's the main point. Is it perpendicular? Now, on that segment, what is the direction of the magnetic force? Up. Up. So nothing happened actually. If you do this, nothing happened. How do you, how come? How come it's not perpendicular? How come it's not perpendicular? It's still perpendicular. Okay? So actually, this is a three-dimensional problem, and it needs you to imagine what happens. That's why we use three-dimensional object in here. I'm not using the board because of that. You have to imagine what happens. Yeah. Yes, I didn't go there yet. I did not go there yet. Okay, guys? So now I'm going to do this. Instead of having this, I'm going to have it something like this. Like this. So now this is the loop. The current is clockwise. Clockwise. Okay? So now, what happens? This segment, that segment, by itself, that segment, like this, can you hold it, please, show it? That segment here, do not look at this because this might confuse you. This segment, and this is the magnetic field. What happens? The force is up. Same goes to the down one. How about that segment? And that's the magnetic field. What's the angle between them? Is that 90 anymore? It's not 90 anymore. So there will be a force on this pushing that in the perpendicular direction, and on the other segment, there will be a force pushing it in the perpendicular direction, and this is what happens. It will start to rotate. If you have two forces opposite in direction acting on this, what happens? It rotates. And it rotates because we have a physical quantity that we talked about in Physics 111. What makes objects to rotate? What makes this, not force. I'll go back. What makes that object to translate, to move in a translational motion? It's force. Only force. What makes object to translate, moves in a translational motion? Only force. What makes object to rotate? It's torque. And if you remember from Physics 111, does anyone remember Newton's first law? Sorry. I'm sorry. Omar, I'm sorry. This is third law, Omar. Second law. Sum of the forces equal to mass times acceleration. This is Newton's second law for translational motion. Newton's second law for translational motion. How about Newton's second law for rotational motion? Does anyone remember it? Did you study chapter 10? Chapter 12? Yes, chapter 10 and 12. Did you take them? Yeah, of course you did. That's one equation for the torque. You're right. That's what it's force cross displacement. That's one form of it. But we have another form of it. That's the centripetal force. I'm saying torque equals. Nope. I times alpha, and I is the moment of inertia, and alpha is the angular acceleration. Torque equal to I times alpha. Alpha is the angular acceleration. Compare those two equations, guys. This is very important that when you look at physics 111, then you, but you were exempted from it, or, right? Which means that you should have known this information. Then you should go back and take physics 111. I is the moment of inertia. Alpha is the angular acceleration. What can any one of you guys tell me what is the meaning of moment of inertia? What does moment of inertia mean? No. To what? Resistance to the
force of light.
resistance to rotational motion. That's torque. Actually, moment of inertia is nothing but resistance to the rotational motion. What's mass? What is the meaning of mass? Resistance to the translational motion. So if that has a mass m, this has a mass m, and I'm going to move it in that direction. If you double the mass, the more resistance to the motion you will have. You will have more resistance to the motion. So mass is nothing but resistance to translational motion. And my famous demo. Now if I would like to rotate this, I see that I have a stone in here, a stone that has a mass of 1 kilogram, and I'm going to rotate it. It's easy, it's not that hard. Now I'm going to put a stone that has 100 kilograms, and I'm going to rotate it. Is it easy? The more the mass, the more the resistance to the rotational motion. That's one. Now let's do the experiment in a different way. I'll have a mass of 1 kilogram in here, and this is the length of that wire, and I will try to rotate it. Is it easy to rotate? Yes, it is. Now I'm going to actually make that length 10 meters. I'll have the same mass. Is it easy to rotate?
No.
It's going to be really hard. So the mass and that distance contribute to the moment of inertia. Moment of inertia, mechanical moment of inertia, that's equal to, if you remember, it's the mass times r squared. You increase the mass, you increase the resistance to the rotational motion, you increase that r, you increase the resistance to the rotational motion. So moment of inertia is nothing but resistance to rotational motion. Guys, I'm going to surprise you and give you one more equation. What is that equation? What we call that equation something. There is Ohm's law. Ohm's law, or that's Newton's second law in electricity. Resistance is nothing but a resistance to the motion of electrons. Look at those. Yeah, in mechanics. Yes, in mechanics. Yeah, the more the potential, that's the result, and this is the cause. So it's just a simple comparison, not really a straightforward comparison. So I just wanted to actually you get the sense of what is resistance. This is the resistance. This is the resistance. Or in electricity also is a resistance. Nothing but resistance. Excuse me. the torque angular acceleration. If I'm going to talk about torque, then I wanted you to know what is torque from Physics 111 before we move on. Excuse me? Yeah, but yes, but if we are going to talk about torque, I would prefer that you would get basic information about torque before we go on to talk about torque in here. That's why I introduced that part from Physics 111. What's confusing? Guys, what's tau? This is a Greek letter called tau. So what is the other tau you're talking about? Okay, time constant. Time constant. So if I tell you torque and I tell you time constant and you see that they are the same because they have the same symbol, then every torque is the same torque. Is it? Okay. As long as you know what's that, there's no confusion. And you know, if you look at the physical quantity that we have, guys, there are so many. So 28 or 30 letters will not be enough to actually to cover all those. That's why we use sometimes the same symbol twice to talk about two different things. Same. Okay. So as long as you know what is that physical quantity, I hope there will be no problem. So torque. If the loop is not perpendicular to the field, if the loop is not perpendicular to the field, then the loop will have non-zero torque and the loop will start to rotate. We have a triangle that has a current I that flows as you see them, and we put that triangle inside a magnetic field. Now, the first question that I'm going to ask you guys, what is the Y component of the force on the wire? What is the Y component of the force on the wire? Is it positive, is it negative, or is it zero?
Y component was positive. Zero. Positive.
Interesting. Negative, zero, and positive.
Zero.
So I did not add none of the above. Zero. Why is it positive? Who said positive? Hussein, you said positive. Ala, you said negative.
Zero.
Why is it negative? Okay. No, you said zero now. Does anyone think that it's positive or negative? Be sure, is it the positive? Zero. How, guys, who's in for negative? Negative. No one? Positive. No one? Zero. Positive? Why is it positive?
Because if we take the side that moves, the current moves in this direction, it has an upward.
Actually, trust me, I know the explanation. And though his choice is wrong, it's not positive, and I know the misconception. But I want you guys to look at the misconception. That's why I keep asking those kind of questions. I want you to look at the misconception. Okay, sure.
It will have an upward
Component.
And the other side is an upward component.
No, it will have, actually the force is going to be in that direction. That one. The force on that side is going to be in that direction. And so the Y component will be in the negative Y-axis. In the negative Y-axis. That's one way to look at it. One way to look at it is like what Bishoy did, is to break that loop into 3 segments and find the forces on each segment of them, then resolve this force on each segment, find the x component and the y component for this, and you will get the answer. And definitely if you do that carefully, you will get the right answer, which is 0. I agree with all of you. That's one way to look at it. Other way to look at it is to go back a little bit and look at what we just said a minute ago. If you have a closed loop, and that loop is the magnetic field is perpendicular to that loop, which is the case in here and the case in here, the net force on that loop was 0. If the net force is 0, that means the x component of that force is 0 and the y component of that force is 0. How come? This is the plane of the loop, right? This is the plane. What is the direction of the magnetic field? Is it perpendicular to the plane of the loop? So this is the plane of the loop. Again, this is the loop, and this is the magnetic field from the floor up. So now the plane is perpendicular to the magnetic field. This is not perpendicular to the magnetic field. This is not perpendicular to the magnetic field. This will rotate. And it will rotate in such a way to minimize what we call it, the energy. Will it rotate? Yeah. Yeah, it's not perpendicular. Will it rotate? Yes, it will rotate. We'll see. We'll calculate the torque. But before I want to calculate I go to calculate the torque, I want you guys to look at this. If you have a loop and the magnetic field is perpendicular to the plane of that loop, it doesn't matter what is the shape of the loop, the net force on it is going to equal to 0. And one of my previous exam, I did this to my students. I said, okay, now you have a semicircle, a loop in the shape of the semicircle, and you have this is the magnetic field. And of course, I do not ask them that straightforward again that I give them in the lecture. I say, now you know that the force on that branch equal to 5 Newton. Calculate the force on this. Actually, I say that the current here is given, the magnetic field is given, I is given, magnetic field is given, and the length, this diameter is given. And from this, we can get that F equal to ILB. We can calculate the magnetic force on this. Then I ask them, I do not tell them that, I give them this information and ask them, what is the force on that semicircle? There is no way that you can do that force on the semicircle without doing a very lengthy integration. Unless you say, well, the magnetic field is perpendicular to the plane, so the force on this should equal to the force in this, but opposite direction. But opposite direction. So you can get 0 magnetic field. And you can simply calculate the magnetic field from on that straight line, then you can get the other one. That doesn't mean that the other approach is wrong. It's actually correct. It's more accurate. It's not more accurate. It's the same accuracy. It's correct, but it takes a little bit longer time. From each one and do the integration from the beginning of the wire to the end of the wire to get the force. So now, Sharif some time ago said that the torque is not only I times alpha, torque equal to R cross F. R cross F. That's why the people who made that door, they were very smart. They know that that door will rotate only if there is torque. So they put the knob somewhere in here to increase the radius, so it will be easy for us to open the door. But if they put that knob in here, now R is small, torque is small. Even if you use the same force, then the torque is going to be smaller. You have to put more force in order to create the enough torque to open the door. So torque equal to R cross F. The cross product tells you that R has to be perpendicular to F. So if I do this, Not all the force that I put to open the door is actually used. Only that component of it is used, but that component is wasted. And you can try this. I can actually, look, I will try to push with a force along that line. Will the door rotate? It will never rotate. It will never rotate because now R cross F, the cross product will give you 0. But if I do this a little bit of an angle and I push, then there is a component. That component is the perpendicular one. So the cross product here tells you that R and F, they have to be perpendicular in order to maximize your torque. So in magnetism, there's the same thing happen. Torque, magnetic torque equal to, in that loop, if we put a loop in a magnetic field in such a way that the plane of the loop is not perpendicular to the magnetic field, we will create torque. The torque in that case equal to R cross F. R, that's R, that's W over 2, and half of that distance, times the force. And the cross product will give you sine of the angle. So you get W over 2, that's R, times F, times sine theta. This is R cross F. And we have two forces acting on two arms in there. That's why we multiply by 2. So the magnetic torque equal to, in that case, W over 2 times F times sine theta. The F here is the magnetic force. And if we go back to the magnetic force was ILP. I'm going to write that equation again in here. And I will leave that equation for the force. Torque equals to 2 times W over 2, width over 2 times the magnetic force times sine theta. I'm going to replace the magnetic force by its value, which is I, L, D, sine theta. I replace the force by its value, which is I, L, and D. L times W, the length times the width. It's the area of that loop. So actually, the torque in that case is equal to the area times the current times the magnetic field times sine theta. I can actually write that in more scientific way. I say that actually it's I times A cross P. I times A cross P. But let's look at this. Oh, yeah, well, yeah. What do you mean by form of vector? Directions? Of course, I have to give you direction. Of course. Of course. Because you're rotating around that pivot. You rotate this. Sorry, I'll take that one. If you rotate it, if you rotate this is going to be the pivot. Because you have force in here and a force in here. You're creating the torque from that force and the torque from that force. That's the two forces. Good question. Here, you rotate this way. So that's the pivot, right? So this is W over 2, and that's the length. The force has to be equal. They have to be equal. Force equal ILP, same length, same magnetic field, same current in the loop. The force. عادية من غير ما لازم يبقوا equal عشان يبقى pivot في النص. No, actually sometimes you force the pivot. Sometimes you force the pivot. Let's talk about this later on. This is not really related here. علاء. Okay, so I said the torque equal R cross P. Sorry, R cross F. Torque equal R cross F. Right? Hassan, in here I said torque equal R cross F. So R, that's W over 2. And the force F times sine theta, that's the cross product. And the 2, because you have two forces. Okay, what is the force? I replace the force by its value. It's I, L, P. This is the force, right? And length times width, that's the area of the loop. Okay? So that's why I replace that by the area of the loop. And we get the torque equal to AIB sine theta. Again, what is theta? It's the angle between the magnetic field and the area. And the area. So this is very important. Theta. It's the angle. We started by having the angle between R and F. And F here, that's why we got theta. Now, when I get that equation, I have to translate that angle to something else, which is, it's the angle between the magnetic field, according to that equation, magnetic field and the area. So now let's assume that if we said, as we said, this is the magnetic field, this is the magnetic field, this is, this is the magnetic field, this is the loop. That's the loop. Sorry, that's the loop. Now the magnetic field is perpendicular to the loop. So the angle between them is 90. What's sine 90? If the loop is perpendicular to B, okay. Sine theta equal to, you're right. Sine 0 is 0, then the torque is 0. So perpendicular to the loop. Okay. Magnetic field, loop. That's confused. Okay, I'll stop it. I'll start this.